Secondary cells. The cells we described in our last lessons are known as primary cells. There is another class of cells called the secondary cells or accumulators. These cells can be recharged by passing current through them in the opposite direction to the discharge. The main advantage of the secondary cell is that they have low internal resistance, unlike the primary cells. They therefore provide large current for a long time with very little drop in terminal potential difference. Examples are lead acid cell used in car batteries and nickel cadmium cells. Key difference between primary and secondary cells. Primary cells cannot be recharged, meaning after use they are dead, so thrown away. Secondary cells can be recharged, meaning they can be recharged after use and used again and again. Irreversible chemical reaction. Reversible chemical reaction. Cheap initially, expensive initially. Small, but for secondary cell, a bit large. Lead acid cell or storage cell. Gaston Plante was a French physicist who invented the first practical version of the lead-acid battery in 1860, the most successful secondary battery of all ages. Gaston discovered that if the charging and the discharging process was carried out a great number of times, the thickness of the lead dioxide layer gradually increased, and the cell was able to supply current for a much longer period. This battery has lead peroxide as the positive plate and sponge lead as the negative plate. The electrolyte is dilute sulfuric acid. In modern commercial practice, the plates are made of grades of lead and antimony placed alternately and separated by thin perforated insulator. All positive plates are connected together to form the positive terminal, and all negative plates form the negative terminal. The entire assembly is placed in a plastic or hard rubber container. While in use, during discharging at the positive plate, which is made of lead peroxide, hydrogen ions from the sulfuric acid are neutralized after acquiring electrons. These ions then oxidize to form water. While the lead peroxide is reduced to a lower oxide of lead, this prevents polarization of the cell. The lower oxide of the lead then reacts with the sulfuric acid to form lead sulfate. At the negative plate, which is made of lead, the lead atom go into solution as lead ions. These ions then react with the sulfate ions from the acid to form lead sulfate on the negative plate as well. As both plates became similar in composition, both coated with lead sulfate, and water is formed at the positive plate, the sulfuric acid then becomes diluted. Its concentration and density decreases. The EMF of the battery also decreases. To maintain good performance, the relative density of the acid and the EMF of the battery should not be allowed to fall below 1.15 and 1.8 volts respectively. At this minimum value, the battery should then be recharged by passing current in the opposite direction to that of the discharge. The battery then regains its original active materials on both plates. At the positive plate, the lead sulfate is oxidized back to lead peroxide. At the negative plate, the lead sulfate is reduced back to metallic lead. When fully charged, the EMF of a lead battery is 2.2 volts and the relative density of the acid 1.25. A battery current capacity is measured in ampere hours. If a battery is rated 80 ampere hours, it can supply 1 ampere for 80 hours, or 5 ampere for 16 hours, or 10 ampere for 8 hours. This is just a rough estimate. The actual capacity is greater at smaller current than at large discharge rates. Care of lead cells. The lead cell should never be left standing in a discharge condition. If not in use, should be charged at least once in a month. Avoid sparks or open flames near the battery because a mixture of hydrogen and oxygen is explosive. Since hydrogen is freely involved from the negative plate and oxygen from the positive plate, this is called gassing. Check electrolyte level regularly if it covers the top of the plate. If not, add only distilled water just to the mark level. Alkaline batteries or nickel cadmium cells. Batteries with alkaline rather than acid electrolyte were first developed by Waldman Jungmann in 1899. Thomas Edison also invented a battery that was to solve the problem of electric cars. In 1901, Thomas Edison and Waldman Jungmann invented an alkaline battery using a solution of caustic potash, that is potassium hydroxide, as the electrolyte, and nickel hydroxide for the positive plate. Edison used iron for the negative plate, and Jungmann used cadmium. Cadmium has certain advantage over iron, and most modern alkaline cells are nickel cadmium, although it is found that a little addition of iron to cadmium improves the efficiency of the cell. Working principle. When the cell is discharging, at the positive plate, nickel 3 oxide hydroxide is reduced to nickel 2 hydroxide. At the negative plate, iron is oxidized to ferrous hydroxide. When charging, the reactions are reversed. When fully charged, the EMF is about 1.4 to 1.5 volts. After some use, falls about 1.3 volts. Advantages of the battery. 1. Very long lifespan. Can last 20 years or more. Durability. Withstand overcharging and deep discharging. 3. Unaffected by temperature changes. 4. Low maintenance. The electrolyte does not deteriorate easily. 5. Environmentally safer, since it does not contain toxic lead or corrosive acid fumes. Disadvantages. 1. Lower efficiency, about 60 to 70%. 2. Low voltage per cell compared to lead acid cells. 3. Expensive to manufacture. 4. High internal resistance, making it unsuitable for very high current output. 5. Takes longer to charge compared to lead acid batteries. Uses: in railway signals, electric lamps and mine lighting, backup power system, electric vehicles. Early models. Many large ships, hospitals, and public buildings are provided with alkaline batteries installation for emergency lighting. I would love to hear from you. Share your thoughts with me. Bye.